Welcome everybody to topic 1.2. That's displacement, velocity, and acceleration. This is daily video 3, and in this video we'll be describing motion using equations for position and velocity as functions of time. We'll develop an idea of what rate of change means. I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut. I know you're wondering, what do we learn? We'll learn a very relevant term, and that term is function. The 3 kinematic equations that you'll learn about in this unit,
Write this down. Video 1.2 Alright.
put us a way to show relationships between position, velocity, acceleration, and time. Well, a function is a mathematical story that tells us how several different quantities are related. So these kinematic equations are functions. They're functions that tell us how position, velocity, acceleration, and time relate. Carefully using algebra is going to let us use those functions and rearrange those functions in ways that can describe those variables in different ways. Let me show you what I mean. Here are 3 functions. They are functions that relate velocity, acceleration, time, and position.
Down.
Here they are using slightly different notation.
That's exactly what my quiz or my test is on. V initial velocity plus acceleration times time. It's the same thing as change in velocity is acceleration times time. Position is initial position plus initial velocity times time plus half of acceleration times time squared. This can be written as change in position is the same as the initial velocity times time plus half of acceleration times time squared. Finally, I have no idea what V2 means. Velocity squared is initial velocity squared plus 2 times acceleration times final position minus initial position, just same as velocity squared equal initial velocity squared plus 2 times acceleration times the change in x.
That doesn't include final and initial quantities, but each row shows us 2 different ways of writing the same relationship. As you can see, let's look at that middle row. That middle row has an x final minus x initial. We're comparing position. On the right side, you can see
middle row
has an x final minus x initial. We're comparing position. On the right side, you can see I've just written delta x. Delta x is the difference between final and initial position. Of course, you can use algebra to rearrange any function in a smart way. These relationships are great descriptions of motion with constant acceleration. Position and velocity with those little subscripts of 0 are the position and velocity values when time equals 0. Sometimes they'll be called x sub 0, x initial, x starting, x naught, which means x subscript 0. Well, what do functions do? Functions describe
Let me check some. Alright.
Motion. They tell a story about motion. So as you can see here, I recorded the position of a cart at various times. Now here's the actual data that I got as the cart was rolling along this track, but you'll notice the time starts at 3.97 seconds. Well, I didn't think that was convenient, so I subtracted 3.97 from everything, wrote down the time since the first point. Now I took that left blue column and that rightmost yellow column, and of course, being a good science person, I graphed them. I graphed all of my data and sketched a line of best fit because I saw a pattern. Now a line of best fit is really useful. It shows the pattern. A line of best fit is also useful because it can be modeled by an equation. As you remember from algebra class, the equation for a line is, y equals mx plus b. The y-axis variable equals slope times the x-axis variable plus the y-intercept. Now, in physics, we like to be a little bit different, so we swap the order of some of those things. Let's talk about the physical meaning of those. The y-axis variable here is position. The y-intercept is the initial position, in this case, about 0.3 meters. The slope I got from this graph was about 0.47 meters per second. Now, meters per second, that sounds interesting. We'll touch on that later. The x-axis variable is just time. So I can use this to create an equation that describes this line. If position is initial position plus velocity times time, I might say x, that's the position, equals 0.3 meters plus 0.47 meters per second times the number of seconds that have gone by. And this equation gives us some predictive power. Now, here's my data again with time and the measured position at that time. I used the equation to calculate some predicted positions. And you can notice that those line up really well. That third column is where the equation said that the cart should be at that time. The middle column is where it was. And there's only a slight deviation on only 2 of those. So that equation definitely describes this motion pretty well. This equation answers a question. It tells us where the cart will be at any time t. But like I said, you can do algebra to rearrange it and answer a different question, like when will the cart be at position x? That bottom function takes an input of x and tells us when the cart will be there. There are some more equations that you should recognize that relate position, velocity, acceleration, and time. The one on top describes the position of an object moving with constant velocity. The one on the bottom describes the position of an accelerating object as a function of time. If you look at it on your AP Physics 1 equation sheet, you might see something like this. Those little subscripts of x just remind us that this is in a particular direction. All right, let's look at something that is accelerating. The position of this spider dog toy starts from rest. The spider dog's position can be described by this equation. X is 0, that's the initial position, plus initial velocity times time, so 0 times time, plus 1/2 times 2t squared. So that's its position. Its velocity as a function of time can be described by that equation. Notice it starts with no velocity and gradually speeds up over time. So here's a table of that spider dog's position and velocity at different times. I'd like to talk about the average value for the velocity of that toy and the value of that toy at certain particular moments. Those are the average and instantaneous values of that toy's velocity. Well, to do that, first, the toy moved 1 meter in 1 second. If it moved 1 meter in 1 second, its average speed was 1 meter per second, but we know it wasn't always moving that speed. It started off at rest. To find its instantaneous velocity, that's the velocity at any moment, we can calculate the average velocity over a small time interval. So here's the data again. We're going to get rid of the velocity data and just look close at this position data. For the small time interval between 0.6 seconds and 0.8 seconds, we can see that the toy moved this really small distance. Well, we can divide that small distance by that small change in time and say at that moment between those times, it had an average speed approximating its instantaneous speed of about 1.4 meters per second. And if we compare that calculation to what the velocity of the toy was, we see, well, yeah, 1.4 falls really nicely between 1.2 and 1.6. If we look at the toy's motion graphically, on the left is the toy's position as a function of time. On the right is the toy's velocity as a function of time. The slope of the position time graph at 0.7 seconds is equal to the value of the velocity time graph at t equals 0.7 seconds. And it's also equal to our calculated instantaneous velocity at 0.7 seconds. The slope of a position time graph, the value of a velocity time graph, and a calculated velocity at a particular time all describe the same thing. So what should we take away? Well, we should know that functions describe motion, and we should be able to calculate average and instantaneous values from a graph or from a table. Thank you very much, folks, for coming along with me today, and I look forward to working with you in our next From a Graph or From a Table.
Welcome to topic 1.3. We're going to be talking about kinematics and representing motion.
I need water. Be right back.
This is daily video 1. In this video, we're going to use a ticker tape graph to represent motion as a number line, a position time graph, a velocity time graph. We're going to use those graphs to get kinematic equations. My name is Wesley Baker. I teach at Creekview High School in Carrollton, Texas. Let's get started. In physics, when we talk about physical phenomena, we use multiple representations to try to display what's going on. That can include descriptions, diagrams, motion diagrams, tables, drawings, graphs, and equations. There are lots of different ways to talk about something that has happened. We want to be as conversant in all of those different ways as we can. So we're going to use multiple representations to talk about motion specifically. So let's look at some of the ones that we're going to get into. When we're representing motion, we're going to start with this object that is covering more and more distance in each time interval. So the first thing we're going to do is just look at an illustration of what's going on here. That car moves farther and farther and farther in each time interval. Another way of looking at how that car moves that can be a little bit more descriptive, it's still a lot like a drawing, is a dot diagram. Now in a dot diagram, a mark is going to be made on the path that the car takes, and that mark is coming down in equal time intervals. What that's going to allow me to do is see how far the car has traveled during that time interval. So here's our dot diagram. And we can see in those equal time intervals, the car is traveling more and more and more distance each time. Now, we can use a ruler, and knowing that that dot is happening each second, we can make a table of our information. And with our table, we can see really specifically where the car is each second. One way of making these dot diagrams is with a ticker tape timer. And a ticker tape timer is a little device that puts a dot on a piece of paper as that piece of paper is pulled through, and it does exactly what we see here with our dot diagram. It shows me how far my object has moved in equal time intervals. I can add to that dot diagram little vectors that show me how far the car goes and in what direction the car travels during each time interval. And so again, we can see here that we are traveling more and more and more distance in each time interval. What we're going to do is take that dot diagram, we're going to build a graph with it. So we're going to take that little dot diagram.
Bro. What the fuck? Holy shit, I'm about to crash out, bro.
The path. That the car takes, and that mark is coming down in equal time intervals. What that's going to allow me to do is see how far the car has traveled during that time interval. So here's our dot diagram, and we can see in those equal time intervals, the car is traveling more and more and more distance each time. Now, we can use a ruler, and knowing that that dot is happening each second, we can make a table of our information. And with our table, we can see really specifically where the car is each second. One way of making these dot diagrams is with a ticker tape timer. And a ticker tape timer is a little device that puts a dot on a piece of paper as that piece of paper is pulled through, and it does exactly what we see here with our dot diagram. It shows me how far my object has moved in equal time intervals. I can add to that dot diagram little vectors that show me how far the car goes and in what direction the car travels during each time interval. And so again, we can see here that we are traveling more and more and more distance in each time interval. What we're going to do is take that dot diagram, we're going to build a graph with it. So we're going to take that little dot diagram with the vectors, and we're going to put it on the y-axis of a motion graph. Now, that vector dot diagram shows me how far the object went in every time interval, and it's representing time and displacement in the same line. What I want to do is just use this y-axis to look at the distance part, and we're going to spread these objects out in time, and so the length of this is going to tell me time of motions that show me how far the car goes and in what direction the car travels during each time interval. And so again, we can see here that we are traveling more and more and more distance in each time interval. What we're going to do is take that dot diagram, we're going to build a graph with it. So we're going to take that little dot diagram with the vectors, and we're going to put it on the y-axis of a motion graph. Now, that vector dot diagram shows me how far the object went in every time interval, and it's representing time and displacement in the same line. What I want to do is just use this y-axis to look at the distance part, and we're going to spread these objects out in time, and so the length of this is going to tell me how far the object went in each time interval. This is a position versus time graph. All we've done is taken that dot diagram and spread it out, representing our equal time intervals with the equal width of our strips of paper. So with this, the length of each arrow is how far the car moved in a given time interval. And that width represents those equal time intervals that we had. So this graph is showing an object with an increasing displacement per unit time. Now, because this is a position versus time graph, the slope of the graph represents the velocity. And what we see here is that the slope is increasing. That tells me that the velocity of the object is increasing as well. The next thing that we're going to do is time and displacement in the same line. What I want to do is just use this y-axis to look at the distance part, and we're going to spread these objects out in time, and so the length of this is going to tell me how far the object went in each time interval. This is a position versus time graph. All we've done is taken that dot diagram and spread it out, representing our equal time intervals with the equal width of our strips of paper. So with this, the length of each arrow is how far the car moved in a given time interval. And that width represents those equal time intervals that we had. So this graph is showing an object with an increasing displacement per unit time.
I think I got what you're saying.
Now, because this is a position versus time graph, the slope of the graph represents the velocity. And what we see here is that the slope is increasing. That tells me that the velocity of the object is increasing as well. The next thing that we're going to do is scoot these lines down, and we're going to compare how far the object went in each time interval per unit time to how far it went in the next time interval. What we're doing is comparing the velocity per time now. So the strips are going to change a little bit what they represent. The length of each arrow is now the change in position per time interval. That's just the velocity. So the length of each arrow is the velocity, the average velocity that the car had for that time interval. The width is still those equal time intervals. And so now what we're looking at is that this graph is showing an object moving with an increasing velocity. The slope of a velocity versus time graph is acceleration. And positive slope here corresponds to positive acceleration for our object. But we can get another piece of information out of this graph, and that's the area. The area of this graph is this right here. That's just the displacement of the object. It's how far it went overall. So the two pieces of information that we can get from a velocity versus time graph are the acceleration, which we get from the slope, and the object's displacement, which we get from the area. We're going to use these two ideas to develop some kinematic equations. So with our kinematic equations, we have three. We use those a lot to predict an object's motion as time goes on. The first one that we're going to look at is this one. Final velocity is initial velocity plus acceleration times time. We're looking at an object that is traveling to begin with, so it has an initial velocity, going to accelerate, so we see a nice positive slope here. We have a final velocity, and it does so in a time of t. So the first thing that we get from this is the idea that the slope of the graph of velocity versus time is acceleration. The slope, when we calculate slope, is the change in the y value divided by the change in the x value. In this case, the change in the y value is the change in velocity, and change in x is the change in time. So because the slope is my acceleration is change in velocity over change in time, or final velocity minus initial velocity divided by time. And I can rearrange this to get this formula. The next thing we're going to do is look at the area of the graph. The area of a velocity versus time graph is the displacement. We're going to use this idea to develop this kinematic equation. So the final position is the initial position plus the initial velocity times time plus 1/2 the acceleration times the time. Rearrange this to get this formula. The next thing we're going to do is look at the area of the graph. The area of a velocity versus time graph is the displacement. We're going to use this idea to develop this kinematic equation. So the final position is the initial position.
Area in a graph is a displacement. And the other thing was, what was the other one? Slope of a velocity versus time graph. Yeah, I need to write that down too. Alright.
The next thing we're going to do is look at the area of the graph. The area of a velocity versus time graph is the displacement. We're going to use this idea to develop this kinematic equation. So the final position is the initial position plus the initial velocity times time plus 1/2 the acceleration times the time squared. Now it's the same graph that we had before, but instead of looking at the slope, we're going to look at the area. So we have area 1 and area 2. Our displacement is going to be those two areas added together. Area 1 is this rectangle, and it's going to be the initial velocity times the time. That's just the length of the rectangle times the width of the rectangle. Area 2 is a triangle, so it's 1/2 the base, which is time, times the height, which is final velocity minus initial velocity.
What the hell?
This piece
Change in x is initial velocity times time.
right here is final velocity minus initial velocity. From this equation, I know that final velocity minus initial velocity is just acceleration times time. I can distribute time, and then knowing that change in displacement is final position minus initial position, we can arrive at this equation. When we look at this equation, it doesn't have time in it, and I'm going to go really quickly through this derivation. We're going to start off with the idea of average velocity, and we're going to solve that for time. So we have time is equal to the displacement over the average velocity. And this is just another way of doing an average. It's my final value plus my initial value divided by 2. We can also use this first kinematic equation and solve it for time. When we do that, we see that time is the change in velocity divided by the acceleration. I can set these two terms equal to each other. I can cross multiply, so I'm going to have 1/2 final velocity plus initial velocity times final velocity minus initial velocity. And that's going to equal acceleration times delta x divided by 1/2. And so it reduces to this. And then if I rearrange that, I can get this equation. So all three of these kinematic equations come from the graph. And we can use these kinematic equations to solve for any of these values. So what should we take away?
Bro, I did not get
Motion can be
any of
represented
that.
in multiple ways. We looked at dot diagrams, we looked at drawings, we looked at tables, we looked at graphs, we looked at equations. The slope of a position versus time graph is an object's velocity. The slope of a velocity versus time graph is an object's acceleration. The area bounded by a velocity versus time graph is an object's displacement. And the area bounded by an acceleration versus time graph is going to be change in velocity. And the kinematic equations come directly from our motion graphs. These are some key things that we should have taken away from this video. Thank you for your time. And remember, you're doing great in physics, and you're going to do great on the AP exam.
Bro, I gotta rewatch that. Holy shit, he did so much manipulation right
X is
here.
the change in time. So, because the slope is my...
message someone. Gotta check when that class works real quick. Where is it at? Alright. Oh my gosh, this class is gonna be the death of me, bro.
My acceleration. Acceleration is change in velocity.
Let me check something.
Velocity over change in time, or final velocity minus initial velocity. Calculates to begin with. We can get from a velocity versus time graph are the acceleration, which we get from the slope, and the object's displacement, which we get from the area. We're going to use these two ideas to develop some kinematic equations. So with our kinematic equations, we have three. We use those a lot to predict an object's motion as time goes on. The first one that we're going to look at is this one. Final velocity is initial velocity plus acceleration times time. We're looking at an object that is traveling to begin with, so it has an initial velocity, going to accelerate, so we see a nice positive slope here. We have a final velocity, and it does so in a time of t. So the first thing that we get from this is the idea that the slope of the graph of velocity versus time is acceleration. So slope, when we calculate slope, is the change in the y value divided by the change in the x value. In this case, the change in the y value is the change in velocity, and the change in x is the change in time. So because the slope is my acceleration, acceleration is change in velocity over change in time, or final velocity minus initial velocity divided by time. And I can rearrange this to get this formula.
This makes sense.
The next thing we're going to do is look at the area of the graph.
Really bad.
The area of a velocity versus time graph is the displacement. We're going to use this idea to develop this kinematic equation, where the final position is the initial position plus the initial velocity times time plus 1/2 the acceleration times the time squared. Now it's the same graph that we had before, but instead of looking at the slope, we're going to look at the area. So we have area 1 and area 2. Our displacement is going to be those two areas added together. Area 1 is this rectangle, and it's going to be the initial velocity times the time. That's
initial velocity times the time. Oh, okay. Initial velocity.
just the length of the rectangle times the width of the rectangle. Area 2 is a triangle, so it's 1/2 the base, which is time, times the height, which is final velocity minus initial velocity. This piece right here is final velocity minus initial.
Let me, oh, you know what? Maybe if I write this down, this might help. So we got a little graph right here. To calculate displacement in a graph. And I'm gonna draw the graph right now. area 2 and since area in a graph is a displacement, so you gotta add the two areas. So you gotta add the two areas together. So length times width for A1, and that's length area of triangle. Triangle formula. So this is not the formula, this is some BS, bro. Base times height. What the hell is HB, bro? Thank you. 1/2 base times height, bro. And what was he saying?
This rectangle, and it's going to be the initial velocity times the time. That's just
V initial times time base height.
just the length of the rectangle times the width of the rectangle. Area 2 is a triangle, so it's 1/2 the base, which is time,
1/2 the base, so time
times the height,
times
which
the
is
height.
final velocity minus.
Oh, I get it. Let's go. Final velocity. Fuck. Initial velocity minus final velocity.
It's initial velocity. This piece right here is final velocity minus initial velocity. From this equation, I know that final velocity minus initial velocity is just acceleration times time. I can distribute
Oh. So this becomes change in x is equal to initial velocity times time plus 1/2 times time times, what is this called? Acceleration times time, which becomes initial velocity times time plus 1/2 acceleration times time squared.
time, and then knowing that change in displacement is final position minus initial position, we can arrive at this equation. When we look at this equation, it doesn't have time in it, and I'm going to go really quickly through this derivation. We're going to start off with the idea of average velocity. We're going to solve that for time.
What is this?
So we have time of average time in it. I can distribute time, and then knowing that change in displacement is final position minus initial position, we can arrive at this equation. When we look at this equation, it doesn't have time in it, and I'm going to go really quickly through this derivation. We're going to start off with the idea of average velocity. We're going to solve that for time. So we have time is equal to the displacement over the average velocity. And this is just another way of doing an average. It's my final value plus my initial value divided by 2. We can also use this first kinematic equation and solve it for time. When we do that, we see that time is the change in velocity divided by.
Divide this. You have to divide it by t. Cancels out. T goes here. T times v. I think you can like subtract. I don't know how you manipulated it. Divide by at. Subtract at. Bring it over here.
By the acceleration. I can set these two terms equal to each other. And I can cross multiply. So I'm going to have 1/2 final
I see what
velocity
he's doing,
plus
but-
initial velocity times final velocity minus initial velocity. That's going to equal acceleration times delta
Why does
x
he do this?
divided by 1/2. And so it reduces to this. And then if I rearrange that, I can get this equation. So all three of these kinematic equations come from the graph. And we can use these kinematic equations to solve for any of these values. So what should we take away? Motion can be represented in multiple ways. We looked at dot diagrams, we looked at drawings, we looked at tables, we looked at graphs, we looked at equations. The slope of a position versus time graph is an object's velocity. The slope of a velocity versus time graph is an object's acceleration.
Slope of position versus time graph is velocity. Slope of velocity first area did by velocity
The area bounded by a velocity versus time graph is an object's displacement. And the area bounded by an acceleration versus time graph is going to be change in velocity. The kinematic equations come directly from our motion graphs. These are some key things that we should have taken away from this video.
Alright.
Welcome to topic 1.3. We're in kinematics and we're talking about representing motion. This is daily video 2. In this video, we're going to use the kinematic equations and velocity versus time graphs to solve for unknown values in motion problems. My name is Wesley Baker. I teach at Creekview High School in Carrollton, Texas. Here are the kinematic equations that we developed last time. They tell us how velocity, position, acceleration, and time work together. For all of these variables, we have the initial velocity in the x direction, that's v0. We have the final velocity in the x direction, that's just a v. That's going to look like vx right here. That shows up in a couple of different places. We have the acceleration, that's an a, time is a t, and then we have initial and final x positions as well. As we solve motion problems with these kinematic equations, there are some guidelines that we need to do as we process verbal information that we have. We're going to get a verbal description of a problem, and we need to extract information from that verbal description. So the first thing that we want to do is go through and identify the known information that we have. So we want to figure out, do we have the initial position? Do we have the initial velocity? Do we have the acceleration? We want to find our known information. Then we want to identify the unknown quantity that we need to solve for. Once we have those two, we're going to...
Yeah, this is actually something smart to write down. Oh, brother, I am in for a long night. Day 3, video 2. Identify known information. Identify unknown quantities. Select the appropriate equations.
We're going to choose the appropriate equation or equations to solve for that unknown quantity. Then we're going to solve for the unknowns algebraically. So, as we're solving for motion problems, when we are trying to find information about velocity, the initial velocity, the speed that we have when we begin, is going to be v sub 0. If an object starts from rest, this initial velocity is going to be 0. The final velocity is just v. If an object comes to rest, or if an object stops, its final velocity is going to be 0. Velocity can be positive or negative depending on the direction in which the object is moving. So you're going to have to look out for that, especially if it says the object turns around or is moving in an opposite direction. When we look at acceleration, the units for that are going to be meters per second squared. So any quantity that you see in a problem that says meters per second squared is going to talk about acceleration.
Interesting. Velocity is meters per second. Shit my neck. Bro, I still gotta do, was it 3 of these? Oh, and then I gotta do 7 of these. Oh my. Actually, wait. My YouTube might be cooked. But I want some music while I'm writing down these notes. Yeah, I'm so. Please tell me that. Oh, no. Alright, good. Wait. Did it cut out? Ah, thank God. My freaking front cover was cooked. What should I listen to? I need like maybe jazz. Oh, let's get one of these live ones going. The coffee shop. Alright, here we go. Let me write this down. Initial velocity is v of 0. If an object starts from rest, its initial velocity is 0. If an object starts from rest, its initial velocity is 0. The final velocity is v. If an object comes to rest, its final velocity. What does that mean? If an object comes to rest. Ah, that makes sense. If its final velocity is 0, and velocity can be positive or negative depending on the direction in which the object is moving.
look at acceleration, the units for that are going to be meters per second squared. So any quantity that you see in a problem that says meters per second squared is going to talk about acceleration. The kinematic equations only apply in situations where the acceleration is constant.
What does that mean?
Part of the reason for that is when we got these kinematic equations, we got them from graphs of velocity versus time where we had a straight line with a constant slope that indicated that we had constant acceleration.
All right.
If an object
Oh, that is a lot of
switches from one constant
words.
acceleration to another constant acceleration, we can break that problem up into separate situations, but we would need to use a separate kinematic equation for each one of those
this makes
situations.
sense.
Accelerations that change are going to require another routine, and we're not going to get into that today. If you are not given the acceleration in a problem,
Oh,
your
no.
problem just got a lot more complicated. So you could find the acceleration first with the equations, then you can find your unknown. So it becomes
Please
a
don't tell me
two-step
I have to
problem.
do that.
Or you can use a velocity versus time graph to solve for your unknown. And we'll look at some examples of that.
Acceleration can be positive or negative. Alright. That is a lot. I don't even know if I want to write that much down. I feel like that's not as important as the velocity stuff. AP Classroom. When I said this was day 3, video 2. Day 3, video 2, continued. If an object switches from one constant acceleration to another. Alright, here I'm gonna write this down instead. Acceleration can only be found when it is constant. If acceleration changes in a graph, a new equation has to be used. To be used. If acceleration is not given, solve for it or use a velocity versus time graph.
Acceleration can be a positive quantity or a negative quantity,
Oh,
and
I
this
gotta write that
depends
down.
on the acceleration's direction. Displacement, the units for displacement are going to be meters. Displacement is the distance
Shoot.
between an object.
Acceleration is meters per second squared. Acceleration meters per second squared. Alright.
To solve for your unknown. The units for displacement are going to be meters.
Displacement is m.
Displacement is the distance between an object's initial and final positions. We can use this equation to get displacement. It tells me that displacement for the change in position is
know this
final
much about
position minus
displacement.
initial position. We don't always have to use final position minus initial position. We can just substitute delta x instead of using that. So those kinematic equations simplify to this. We can just
Holy.
write delta x instead of x minus x0. Displacement, because it's a vector, can be positive or negative. Time is probably the easiest quantity to
Time.
talk about and the easiest quantity to identify. It's measured in seconds, tells me how long this takes place, and time can only be positive.
Time is only positive.
So let's practice using these equations to solve for some unknowns. For our first question, we have a car driving down the road. It's going to slam on the brakes and stop over a distance of 30 meters in 6 seconds. We want to know the car's initial velocity. This is my
I want to solve this before. Oh crap, I have this review packet. Oh my lord. Oh nah, this packet does not look good. I don't know how late I'm gonna be up doing this.
Given information, the car
A car driving down the road slams on the brakes and stops over this. Car's initial velocity. Distance. I'm actually, how many questions? Alright, looks like he does 2. I'm gonna just watch him do.
car
this first
stops,
one.
so the final velocity is 0 meters per second. It does all of this over a distance of 30 meters,
Write
and
this
it
down
takes
in
6.
my notebook real quick. Write this as an example. EX1. Alright. Car drives down road. Stops over distance of 30 meters in 6 seconds. Car initial velocity question. So they give us crap.
Seconds. So I know these 3 pieces of information, but I don't know the acceleration, and I don't know the distance of 30 meters velocity. This is my given information. The car stops, so the final velocity is 0 meters.
Oh, that makes sense. Final velocity would be 0 meters per second if it stops. The position, or the change in change in position is 30 meters. That makes sense. And the total time is 6 seconds.
Per second. It does all of this over a distance of 30 meters, and it takes 6 seconds. So I know these 3 pieces of information, but I don't know the acceleration, and I don't know the initial velocity. Because I don't know the acceleration, this just got complicated. So we're going to look at solving this problem in 2 different ways. The first way is completely algebraically using the equations. So here are my equations. Because
Yeah, we're given our equations on the exam. We got a of x is unknown, so acceleration is unknown, and final, or is that initial? Initial velocity is unknown.
I don't know the acceleration, and because I don't know the final velocity, I'm going to have to combine 2 of these equations to find my answer.
Are you serious?
So we'll start with this kinematic equation, and we'll solve.
Let me write this down then. Choose an equation. We'll write down the 3 below. V equal initial velocity plus acceleration times time. Oh, my nose is so stuffy. Change in position is initial velocity times time plus 1/2 a x t squared. Velocity squared initial plus 2ax delta position.
Solve it for acceleration. So acceleration is negative initial velocity divided by time. I'm going to substitute that into this kinematic equation, and then I can simplify
Okay,
it.
what the heck?
To have to combine 2 of these equations to find my answer. So we'll start with this kinematic equation.
He's using a velocity equation.
And we'll solve it for acceleration.
So he takes the initial equation, takes this one, v equal v initial plus acceleration times time. Then he manipulates it. What the heck does he do? How does he manipulate it into this? If he were to divide by t, or if you were to subtract this to this side, it'd be v minus what? Oh wait, since v is 0, is that why? And he subtracted that. I hope that's why. Whatever. So he takes, since this is 0, he just subtracts this, so negative v initial, and then that leaves a, and then all of that's over t because he takes a t away.
Acceleration is negative initial velocity divided by time. I'm going to substitute that into this.
And then he subs it into, that is so nasty. And then he subs a into sub in, I don't even
kinematic
wanna.
equation. And then I can simplify it. And now I can solve for the initial velocity. There's a lot.
This is so disgusting. And these two t's cancel out. So now we have v initial times time plus 1/2 times negative initial velocity times time over time squared. These two cancel out. That's still initial, right? Yeah, initial velocity times time plus 1/2 minus times t. Oh my lord.
A lot of algebra involved in this. The initial velocity is going to be 2 times the displacement divided by the time. The initial velocity comes out to be 10 meters per second. This is
What the hell? How the hell did you get that? Initial velocity. Wasn't this change in position? Did he manipulate it even more? What the hell?
There's a lot of algebra involved in this. The initial velocity is going to be 2 times the displacement divided by the time. The initial velocity comes out to be 10 meters per second. Involved in this. The initial velocity is
Initial velocity. My gosh, what? This doesn't make sense. How did he jump from that? What? Initial velocity is 2.
is going to be 2 times the displacement divided by the time. The initial velocity comes out to be 10 meters per second. This is a really complicated way to do the problem. I would much rather do the problem using a graph of velocity
I
versus
don't even
time.
know how we got to that. I'm gonna just write this down real quick. This freaking delta was in all of these, and then he just took delta out last second. That does not make sense. And then delta gets subbed in somehow in here. Over time equals 10 meters per second.
Meters per second. This is a really complicated way to do the problem. I would much rather do the problem using a graph of velocity versus time. So we have the same given information, but now we're going to look at the velocity versus time graph. I know that I start moving, even though I don't know what that velocity is, and over a time of 6 seconds, come to stop. Now, because this is a velocity versus time graph, I know that the slope of this graph is acceleration, and I know that the area of this graph is the displacement. Well, I'm not solving.
We know slope of velocity versus time graph equal A, and area of velocity versus time is displacement.
For the acceleration here. So I'm going to use the area. I know the area is displacement, and I know that my displacement is 30 meters. So area of a
Area equals position. Position equal 30 meters.
triangle is 1/2 base times height, and that area is equal to delta x.
Oh
so I
my
can just substitute
Gosh.
delta
Oh,
x instead of using that. We have those same two facts where the slope of the graph is the acceleration and the
this is
area
so
of the graph
stinky.
is the displacement. Again, we're going to use the area here to figure out what's
Whoa,
going
oh, this is
on,
the wrong
and it's the
quote.
delta x.
Area equals delta x. Delta x equal 30 m. Area. Oh my gosh. 1/2 times t times v initial equals delta x. V initial equals 2 delta x over t 10. He knows. I thought area. Is area really just delta x? I don't remember this being true. I remember this being two. What that 2 times 30 over t, and t is. Alright, that doesn't
I can
make
solve
sense.
this for my velocity really easily. That velocity is 2 delta x over time. So I can do 2 times 30 divided by 6, giving me a velocity of 10 meters per second. Let's look at another example. Here we have a sports car.
Alright, I'm gonna try and do this one on my own. Oh, this is gonna be so bad. Sports car starts from rest. Starts from rest means initial velocity is 0. Accelerates. So we got final velocity equals 27 meters per second. And the time is equal to 11.8 seconds. What distance does the car travel? So we're looking for distance. I need my graph, my physics sheet. It's a key. Where is my physics kinematics equation sheet? It's at the very back. Yeah, this is definitely it. Alright. We got acceleration, we're trying to look for the distance. And there is nothing on distance on here, what the heck? What distance does the car travel in this time? You know what? X position, final position is initial position. Well, we do know initial position is 0. Or I'd assume it'd be 0, right? Shit.
Are starting from rest and accelerating to a final velocity of 27 meters per second in 11.8 seconds. And I want to know the distance the car travels in this time. Let's look at our knowns. So given information that we have, I know that my
Final velocity, yeah, 27 meters per second, I have that.
final velocity is 27 meters per second. I don't know how far I go. That's my unknown. And I know it takes 11.8 seconds. I don't know the acceleration, but I do know that I start from rest.
Alright, we don't know acceleration. I forgot to include that. And we don't know our initial position.
So again, I don't know the acceleration in this problem. So it got a lot more complicated. The first way that we're going to look at solving this problem is using the kinematic equation.
Why can't we just skip to the graph? I thought we all agreed that graph was easier.
We'll start here.
Do we even have everything to fill this out? 27 equals... No, because then we have to freaking sub in A again.
And from
And
here,
make
we'll
it
solve for
stinky.
the, find the acceleration as 2.29
Wait,
meters.
oh, he got
So the
that.
acceleration,
Oh, we do have that to do that. Alright, never mind. V initial plus A times T, manipulate that so A equals negative V initial over T, right? Wait. Swear to God, this guy is actually freaking messing with me. A equals final velocity minus initial velocity over T. Final velocity 27. Initial velocity is 0 minus 0 over time 11.8. So our acceleration is wrong thing. And he gets this right.
is the change in velocity over time. I have both of those velocities, so I can find the acceleration as 2.29 meters per second squared. Then I can take that acceleration and plug it into
What is... Bruh.
another kinematic equation with my nose.
We change a position.
And I get the displacement as 159.
Wait a minute. I have a mini equation down here, and it says that the change in position is equal to 0 plus 27 over 2 times 11.8. No way this works. 27 divided by 2. 27 over 2 times... I don't think I can copy paste on the SAT version. Times 11.8. 159.3. What? Why the hell? Bro, there was no reason for me to do this. Oh, nah. What? What? Initial or... Bro, what? This mini equation saved my life, bro. What? There was no need to do all this. Let me try doing this one though. If you take the initial velocity, our initial velocity is what again? Is 0 times time. What? Oh wait, no, that makes sense. This cancels out because it becomes 0. 1/2. Yeah, this mini equation, bro.
Meters. Again, that's a lot of algebra. It takes 2 steps to do so. I much prefer the second method of using a velocity versus time graph. Same
Me
given
too, buddy.
information,
Me too.
but now we have a velocity versus time graph. This graph has the same given information that we have, right? We start off at rest, we end at 27 meters per second, and it takes place over a time. So we have this nice triangle here. We have those same 2 facts where the slope of the graph is the acceleration and the area of the graph is the displacement. Again, we're going to use the area here to figure out what's going on. And since we're solving for the displacement, we're just going to solve for the area of our graph. So the area is displacement. This is a triangle, so it's 1/2 the base, which is time, times the height, which is the final velocity. That's going to be equal to my displacement. So we're going to take 1/2 times 11.8 times 27. When you put that in your calculator, you end up with 159.3,
This
just
makes
like we had
sense.
before. So what should we take away from what we did here? We can solve
feel like a
kinematic
genius.
problems in one dimension, just moving along a straight line, using these kinematic equations and using that method of identifying our knowns, finding our unknowns, picking an equation, and then substituting numbers into it. We can also solve these problems using a velocity versus time graph because we know that the area of the graph is displacement and the slope of the graph is acceleration. Thank you for your time. And remember, you're doing
1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, brother.
Welcome to topic 1.3. We're representing motion. This is daily video number 3, and in this video, we were going to analyze the special case of free fall near the surface of a planet or moon. We'll calculate the launch speed of a projectile based on its time in the air. I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut. And first, let's just start with a really big, important, relevant term, and that's the idea of free fall. An object moving through the air is affected by many forces. But if gravity is the only significant force acting on the object, we can neglect the other forces. For example, if air resistance is negligible, then objects falling near the surface of a planet move with the same acceleration, regardless of any other factors. If an object is moving and gravity is the only significant force exerted on it, then we can say the object is in free.
Time to write more notes. Oh, man. I'm gonna go to sleep with my brain when I start like going insane, bro. Today, 1.3, daily video 3. AP Classroom, day 3, video 3. Free fall. Object is moving. Object is moving, and we only account gravity.
Fall. Here on Earth, that means the object is moving with a downward acceleration of round about 10 meters per second squared. So its velocity gets 10 meters per second more down every second. Regardless of how fast an object in free fall is moving or in what direction it's moving, its velocity is always getting 10 meters per second.
I guess that means everything moves down at 10 meters per second squared dash so every second times 10. I don't know if that's how it works. That doesn't make sense.
More downward every second. So we're going to look at an object right now, 1 second later, 2 seconds later, and 3 seconds later. If right now an object is moving 13 meters per second upwards, 1 second later it would only be moving 3 meters per second upwards. That's 10 less. Well, 3 up minus 10 is 7 meters per second downward, and then 3 seconds from now, it would be moving 17 meters per second downward. That's a change of 10. 10 more down every second. So
it's
free
plus
fall is falling in the absence of air resistance. Now on Earth we have air, but let's go to the moon. So since there's no air in the way when something falls on the moon, all objects would fall with the same acceleration. And we're here to talk about the very specific case of free fall near the surface of planets or moons. So if we use our moon as an example, it's going to be really convenient. Now, if an astronaut on the moon were to drop some objects, that's any objects at all, those objects would all fall with exactly the same acceleration, regardless of their shape, color, shininess, material, weight, temperature. Let's pause on that for just a second. The same acceleration doesn't mean that those objects will always have the same speed during their entire fall. When an object is dropped, that means its initial speed is 0. A falling object speed...
That seems like important, right? When an object is dropped. initial speed is 0.
Speeds up faster and faster as it falls, so that's definitely not constant speed. Constant acceleration means that any falling object speeds up by the same amount every second. So here are two objects falling on the moon. The famous hammer. So here are two objects by the same.
Constant acceleration means any falling object speeds up by the same amount every second. Constant acceleration speed up by same amount every second.
Same amount every second. So here are two objects falling on the moon. The famous hammer, the feather. They're both speeding up at the same rate. So let's graph that. First off, you see a graph of a falling object's height as a function of time. Because there's a constant negative acceleration. We can see the slope of that height graph getting steeper and steeper and steeper as time goes on. On the moon, that downward acceleration is around about 1.6 meters per second every second. Now, you don't need to know that for the exam, just for this example. Here's a graph of its velocity as a function of time. Notice that the slope of the velocity graph is negative 1.6. The slope of the falling on the moon, the famous hammer, the feather. They're both speeding up at the same rate. So let's graph that. First off,
this is the height.
You see a graph of a falling object's height as a function of time. Because there's a constant negative.
So this is the velocity, or this is acceleration. Oh, but acceleration will always stay constant. In free fall, acceleration is constant. So this is a constant. Where was the example of 8 that we had the other time? Fuck. 8. It's going down.
Acceleration. We can see the slope of that height graph getting steeper and steeper and steeper as time goes on. On the moon, that downward acceleration is around about 1.6 meters per second every second. Now, you don't need to know that for the exam, just for this example. Here's a graph of its velocity as a function of time. Notice that the slope of the velocity graph is negative 1.6. The slope of the velocity graph is the value of the acceleration versus time graph. And that position time graph
does make sense.
Gets steeper and steeper. The velocity gets faster and faster.
This gets steeper and steeper, velocity gets faster and faster.
The acceleration is a constant negative 1.6 meters per second squared. The speed of those falling objects was increasing, getting faster and faster by 1.6 meters per second every second. It's downward, so
gaining.
I've assigned a negative direction to that. The slope of the position versus time graph is initially 0 and then gets steeper. The free fall acceleration of objects is different on the surface of different planets. In most situations you'll deal with in this course, air resistance is negligible, but that's not always the case. Here, I have two pieces of tissue paper with the same mass that are obviously quite different. This one's all wadded up into a ball, and they fall very differently here on Earth. It just hit the ground now. Now, here's one quick screen grab from that video. You'll notice that the dense ball is falling with an acceleration of about 10 meters per second squared, but that yellow sheet is definitely not. It is slowed by the air, even though they're the same mass. As you just saw, for that wadded up tissue paper ball, the effects of air resistance are very small. In fact, throughout this whole course, you could ignore the effects of air resistance unless it's otherwise mentioned. In this course, it's safe to just use 10 meters per second squared as the downward acceleration for any falling object near the surface of Earth. Because for most everyday objects, they fall for only a few seconds. So the effects of air resistance are small, and for our purposes, We're just going to ignore those effects. So let's compare dropping something and throwing it. In this example, I'm dropping a pineapple over and over again. When I let go of the pineapple, it has an initial velocity of 0. Its speed increases as it falls. Well, my office is on Earth, so the acceleration here is about 10 meters per second squared downward. But if I also had an office on Mars and I was dropping pineapples there, that would raise a lot of interesting questions, not the least interesting of which would be how fast do they fall? Well, let's figure it out. On Mars, the acceleration is less than on Earth. So let's figure it out. We're going to graph the position of an object dropped on Earth as a function of time. There's the data right there, and there's what the graph would look like. I'm sure you've already created a graph like this in your class.
Oh, wait, isn't gaining by 15? Alright, it is.
Well, we're going to do the same for Mars, where the acceleration is a little bit less than the acceleration that we have here on Earth, a little less than half as much. So there's the data for Mars. You don't need to know these numbers off the top of your head or anything, but that's what the graph would look like for a free-falling object on Mars. So notice that in the same 4-second time window, in the same interval, an object on Mars doesn't fall as far.
Well, let me try and understand this. So, is it falling on Earth? What's the height? Bruh. This is the acceleration. Alright, the acceleration will usually always be constant unless it changes. Alright, this makes sense. Our velocity is probably going to be like this again, right?
But the shape of its position versus time graph is the same as on Earth, just scaled differently. That's the shape of a falling object undergoing constant negative acceleration. So let's take a look at the velocity versus time graph. On Earth, that velocity changes by 10 every second. So a velocity versus time graph of a falling object on Earth would have a constant negative slope. Notice the acceleration versus time graph has a constant negative value. For an object falling on Mars, there we go. The acceleration of a falling object on Mars is about 3.7 meters per second squared. A falling object speeds up by only 3.7 meters per second every second when falling on Mars.
Yeah.
So the slope of the velocity versus time graph on Mars is not as steep as the slope of the velocity versus time graph on Earth, because the acceleration of a falling object on Mars is not as much as the acceleration of a falling object on Earth. When we throw something upwards, we throw it up with an initially very fast velocity that decreases to 0 at the tippity top of its path. But notice the acceleration of that object is always 10 and always down. Even when we throw something at an angle, the vertical acceleration on Earth is always 10 meters per second squared all the time and always down. The ball's vertical velocity changes, but its horizontal velocity remains the same. In my class, one of my students' favorite activities is launching air rockets, and I'd like to go through a quick example of that with you. Here, you see an air-powered rocket. We can launch it up in the air and let it come back down. We can time the whole flight. So, for example, if this air rocket were launched with a speed of 20 meters per second upward, it would take 2 seconds to reach the top of its path. It would take 2 seconds for gravity to stop it, because gravity slows it down by 10 every second. So if it takes 2 seconds to go up, it takes 2 more seconds to fall back down. That means the rocket would be in the air for a total of 4 seconds. Well, on the way up, the average velocity of the rocket is the average of its speed at the top and its speed at the bottom. The average of 20 and 0 is 10, and it spends 2 seconds going up. So if a rocket spends 2 seconds moving with an average speed of 10 meters per second, the rocket's maximum height is 20 meters. Here's that whole setup again for a faster rocket launch. If the rocket had been launched at 30 meters per second, well, it would definitely take more time, 3 whole seconds, to get to the top of its path. That's 30 divided by gravity. It would take 3 more seconds to fall back down to Earth, for a total of 6 seconds in the air. Its average speed on the way up would be faster. The average of 30 and 0 is 15. Average speed times time is displacement, giving us a maximum height of 45 meters. So I've got a question for you. I've blanked a lot of useful stuff out.
Oh.
It would be awesome if you screenshot this slide and the next one. I'm going to put the solutions up, but try to figure it out. Grab a screenshot of this one and a screenshot of this one with the worked answer.
I didn't look.
It would be...
Let's see. for launch 35 meters per second. This tells us something. If the this and this can be same XS, XS, 2XS.
Be awesome if you
I would
screenshot
listen
this
to it.
slide and the next one. I'm going to put the solutions up, but try to figure it out. Grab a screenshot of this one and a screenshot of this one with the worked answers, and then riddle me this.
Alright. What the hell? Oh, wait. If it's meters per second. Oh, wait. He's talking about how it's freaking everything is, what's it called? Everything is 10 meters per second. Average velocity is gonna always be 10 meters per second. So 3.5. Yeah, let me fill the blanks in on a different sheet of paper. I promise I did not look at the. So we got first blank is gonna be 3.5 s. Second blank is gonna be 3.5 to come down. Total is gonna be 7 seconds. Average rocket speed on the way up is wait, what about this? I'm confused about this now. Isn't this 35? So the rocket goes up for 3.5 seconds. Rocket's maximum height is wait, isn't it just 35?
Figure it out. Grab a screenshot of this one and a
Okay, what the hell? 3.5, total 7 seconds. Average 0. The rocket speed on the way up is 17.5 meters per second. 17.5. And the rocket goes up for 3.5 seconds. So maximum height is 61. Bro. Average speed times time. Oh my gosh.
screenshot of this one with the worked answers, and then riddle me this.
I catch this pineapple 20 seconds after I throw it. Pineapple is initial velocity. Bro, what is up? What could the pineapple's initial velocity be? Wait, maybe we got a physics equation we can use. Final velocity is initial. Oh my gosh. I'm dead.
Here's one for you to try. Teachers out there, ask your students this question. See if they can calculate the launch velocity and maximum height of that pineapple. All right, I've got some review questions for you. A carrot is thrown upward, a line is thrown downward. Which statement is correct? Well, take a look at the statements. I'll wait. All right, well,
a carrot is thrown upward, a limestone downward, which the carrot's acceleration is greater. The limestone. Oh, I already spoiled myself it. Apparently it's both. But isn't it going to be 10? 10
and is thrown downward.
So that's why
Which statement is correct? Well, take a look at the statements. I'll wait. All right. Well, it can't be the first or second one because once they're released, their acceleration is the same.
I'm gonna write that down. That seems important to write. When something is released, the acceleration is the same.
what if a carrot is dropped from rest and a line is thrown downward? Which of
A carrot is dropped from rest while a lime is thrown downward. Acceleration is greater for the lime, I think. Yeah, acceleration. I feel like the initial I think the initial acceleration would be faster for the lime, but then it evens out.
these statements is correct? The carrot is just dropped, but the lime is thrown. The lime definitely has a faster initial velocity. But they have the same acceleration. Well, what if we were to take that dropped carrot and thrown lime and draw their motion on a velocity versus time graph? Which one would have a steeper slope? The lime that's thrown or the carrot that's dropped?
What's he asking?
And draw their motion on a velocity versus time graph. Which one would have a steeper slope? The lime that's thrown or the carrot that's dropped?
Steeper slope, lime that's thrown, or carrot that's dropped. I have no idea, bro.
Well, I know that the slope of a velocity time graph is acceleration, so of course they would have the same slope. But they would be different. If the line were thrown downward, its velocity versus time graph would start with a lower y-intercept, a lower initial velocity. All right, what should we take away? What's the important take-home message here? We learned about free fall without air resistance and even some free-falling tissue paper where there was air resistance. We looked at dropped objects versus thrown objects and even did the math for some vertically launched projectiles. Thank you so much for coming along with me and hopefully working some of those practice problems, sketching some graphs, and figuring out that free-falling objects have the same downward acceleration.
Why is my freaking notebook being so dumb?
Alrighty, folks, thank you very much. See you next time.
Why is it built like this? What the heck? Why are the pieces coming off? What the hell? Oh my lord, bro, my notebook is falling apart. Holy crap, I'm not even done through 1.3. Is he gonna go? Oh, the timer never went off. See, I do for 30 minutes. .3. What am I labeling? What am I labeling? AP Classroom Day 3, Video 3. AP Classroom. Video 4. Holy crap. 1, 2, 3, 4, 5, 6, 7, 8. That is not what I meant to do. What the heck? Bruh.
Welcome to topic
Oh,
1.3.
my
We're going to be talking about kinematics and representing motion. This is daily video number 4. In this video, we will create position, velocity, and acceleration versus time graphs from an object's motion and show how the graphs describe that motion. My name is Wesley Baker. I teach at Creekview High School in Carrollton, Texas. As we're talking about motion graphs, I want to remind you of a few things that we already know. Graphs of position, velocity, and acceleration versus time can all describe the same motion. The slope of a position versus time graph is velocity. The area bounded by an acceleration versus time graph is the object's change in velocity. So that's how a position versus time graph and an acceleration versus time graph can tell us about velocity. The slope of a velocity versus time graph is acceleration. And the curvature of a position versus time graph will also give us information about acceleration. The area bounded by a velocity versus time graph will tell us an object's change in position. So we're going to keep all of these things in mind as we look at 4 different kinds of motion. In this first one, we have an object moving forward and speeding up. There's the little dot diagram that we had with the little vector arrows for each time interval. We're going to spread those out in time so we get a nice position versus time graph. And so what we see here from the position versus time graph is that the car is moving forward and it's covering more distance every time. It's speeding up. We're going to draw a line connecting the tips of those. And what we see is that the rate of change in position increases as time goes on, which means the slope of our position versus time graph increases as time goes on. Now what we're going to do is compare those individual rates of change or compare those slopes. So we've got a velocity versus time graph now, and we can see really clearly that the velocity is increasing in the positive direction as time goes on. If we add a little line there, because we know that the slope of this line is acceleration, we have a positive slope, we can say that the car has positive acceleration. So we can look at all 3 of those graphs together. This is our position versus time graph. This is the velocity versus time graph that corresponds to this. And this is the acceleration versus time graph. All of these things are true, and these are the 3 motion graphs that go together for this car's motion. For our second motion, we're going to have the car slow down. So the car is moving forward and slowing down. We're going to throw up that dot diagram and spread it out in time to give us a nice position versus time graph. I'm going to draw that line to see what's going on all the way through. And what we can see is that the rate of change, how my position versus time changes, is decreasing. Those little strips are getting smaller and smaller. We can also see that the slope of this position versus time graph decreases. It starts off very positive here, and it's less positive there. So the slope is decreasing. We can take and now compare all of those little rates of change to each other. So we've got a velocity versus time graph now. And as we can see, the velocity is decreasing, even though it's still in the positive direction as time goes on. We'll add a little arrow so we can see the slope very clearly. And we can see that we have a negative slope, so we have a negative acceleration. If we look at all of those graphs together, it says the same thing. And each one of these graphs tells me what's going on here, right? I have that nice curve with a downward slope and a negative acceleration that goes on with it. I have a decreasing velocity versus time. For our next motion, instead of moving forward, we're going to move backwards. So for this motion, we're moving backwards and we're slowing down. So the car moves backwards and it slows down. We're going to throw up the dot diagram again, then we're going to spread that out in time to get a position versus time graph for this motion. Notice again, we're moving backwards. So we're going to add that line so we can see the slope more clearly. The rate of change of position decreases as time goes on. We're traveling less and less distance, even though we're going backwards as time goes on. And this part's a little bit tricky. The slope of the position versus time graph increases because it's becoming more positive. So a better thing to say is that the slope of this graph becomes more positive as time goes on.
I was literally just looking at my screen and not even listening to what I was saying, bro.
Slows down. We're going to throw up the dot diagram again, and we're going to spread that out in time to get a position versus time graph for this motion. Notice again, we're moving backwards. So we're going to add that line so we can see the slope more clearly. The rate of change of position decreases as time goes on. We're traveling less and less distance, even though we're going backwards as time goes on. And this part's a little bit tricky. The slope of the position versus time graph increases because it's becoming more positive. So a better thing to say is that the slope of this graph becomes more positive as time goes on. It starts off as a very negative slope, and then it gets less negative, even though we're going backwards. I'm going to spread that out in time to get a position versus time graph for this motion. Notice again, we're moving backwards.
Car moves backwards.
We're going to add that line so we can see the slope more clearly. The rate of change of position decreases as time goes on. We're traveling less and less distance, even though we're going.
Change decreases as time goes on. Yeah.
going backwards as time goes on.
Slope of the position versus time graph increases. This doesn't make sense. It's going down negatively. How's it getting increasing? You know what? It's negative. And since it's going down, it's becoming positive because it's approaching 0.
And this part's a little bit tricky. The slope of the position versus time graph increases because it's becoming more positive. So a better thing to say is that the slope of this graph becomes more positive as time goes on. It starts off as a very negative slope, and then it gets less negative. That's an increase. Now, if we compare those rates of change to each other, just like we did before, we're going to scoot that up to the time axis. But we can see that my velocity is getting smaller. It's getting more positive as time goes on. And if we throw up that line to look at the slope, we can see that the car has a positive acceleration. Even though it's moving backwards, it has a positive acceleration because the direction of the change in velocity is towards the positive direction. This is a positive acceleration. So we can look at all of these together. Car moves backward and slows down, has a positive acceleration. There are two things here that tell me we have positive acceleration. One is that the curvature of this graph is positive. If we wanted to, we could put 2 dots here to make a little smiley face to remind us that it's positive.
Concave
But if
up.
this curvature is positive, it's telling me that this motion from the position versus time graph has positive acceleration. We can also see we have positive acceleration here because even though the velocity is negative the whole time, even though we're moving backwards, this line has positive slope. We have our last motion. This time we're going to speed up as we move in the backwards direction. There's our dot diagram. We're going to spread that out in time. So we have our nice position versus time graph here. We're moving backwards. We're speeding up. Here's our line. And so the rate of change in position increases as time goes on, right? We're going further and further and further as we go backwards each second. The slope here is decreasing because it's becoming more negative. I start off here with a slightly negative slope, and it gets more negative as time goes on. So the slope here is decreasing,
So
even though we're speeding up.
acceleration-
And again, we can see this better with the velocity. The velocity is increasing in the negative direction as time goes on. And we throw up a line to look at the slope, and we can see that that slope is negative as well. So the car is going to have a negative acceleration. Look at all three of those together. Again, we see here that we have a downward curve. We put the 2 dots there. That face would be frowning. That's negative curvature, telling me I have a negative acceleration. Same thing with the velocity here. It's a negative slope, negative acceleration. We can also group these by the kind of acceleration we have. Both of these motions show that I have positive acceleration. I can see on the position that I have positive acceleration because both of those have upward or
concave
positive
up always
curvature.
means
That corresponds to positive acceleration. I can also tell that this is positive acceleration because both of the velocities have positive slope. And then with negative acceleration, each object's moving in a different direction, but we can see from the position graphs that we have negative curvature, they're concave down, frowning, giving us negative acceleration. And then at the slope of the velocity versus time graph, even though one object is moving backwards and the other object is moving forward, the slope is negative, so I have negative.
Hold up. Object moving in the positive direction. If it's positive, velocity gonna be same.
Negative acceleration there as well. So what should we take away? Here are some quick takeaways. Graphs of position versus time, velocity versus time, and acceleration versus time can all describe the same motion. The slope of a position versus time graph is velocity. We can also get an object's change in velocity from the area underneath an acceleration versus time graph. The slope of a velocity versus time graph is acceleration, and the curvature of a position versus time graph will also give us information about acceleration. And the area underneath a velocity versus time graph tells me an object's change in position. Thank you for your time, and remember, You're doing great in physics, and you're going to do great on the AP exam.
Oh my god. There's another one. 1, 2, 3, 4, 5, 6, 7. Oh, brother.
Welcome to topic 1.3, that's representing motion. This is daily video 5. In this video, we will describe motion when acceleration and initial velocity are in opposite directions. So a motion like this, and then we'll do it again using a toy car. I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut, and welcome to a very tropical AP Daily. We're going to have to start by discussing some relevant
I
terms.
wish, bro. Quit playing with me. 19 minutes.
And the first of those relevant
I might
terms
just do one
is
more.
free fall. If an object is moving and gravity is the only significant force exerted on it, then we say the object is in free fall. Here on Earth, that means that the object is moving with a constant downward acceleration of about 10 meters per second every second. That means its velocity gets 10 meters per second more
Let me
down.
check something real quick. Hold up.
Every second. Regardless of how fast or in what direction an object in free fall is moving,
Why is it not? Ooh, I guess it
its
was
velocity
working.
always becomes 10 meters per second more downward every second. So here we see an object that's rising really quickly. After a moment, it's rising slowly. At the very top of its path, it's momentarily at rest. A moment later, it's falling slowly, and a moment later, it's falling really quickly. If all of those were separated by just 1 second, the difference in those velocities would be 10 meters per second more downward every second. Every moment, the velocity vector is more down.
Look at this packet I have. Fall. Drop that V initial. Thumb vertically up down at V initial. Free fall acceleration. Gravity is 9.0 meters per second. Tennis player serves tosses the ball straight up while the ball is in freestyle. Well, reasoning. Oh my gosh, this seems so terrible, bro.
So we're going to take a look at a video of me tossing a pineapple up and down like you just saw. Here it is. There's me in just a lovely shirt tossing a pineapple. I know. Let's see that just one more time. What I'd like you to notice is that the pineapple slows down as it goes up.
I'm so confused. Brother. If I don't finish this, I feel like I won't touch this after the test. And this is key knowledge for me to know. I don't want to do this, bro.
Which is the tippity top of its path and then speeds up as it falls down. So let's look at some different phases of that pineapple's motion. At first, the pineapple's velocity is upward. The acceleration is downward, so the pineapple is slowing down. At the tippity top of its path, the pineapple's velocity is momentarily at zero. The acceleration is still downward. Earth is still reaching up and pulling down on that pineapple, changing its velocity by 10 meters per second every second, but for just a moment, the velocity is zero. Well, on its way down, yeah, the acceleration is still downward, but on the way down, the speed increases. The velocity is downward and getting faster. So I went ahead and graphed the motion of that pineapple. I graphed the motion for the first part of the motion as the pineapple was rising, and then the second half of the motion as the pineapple was falling. Let's take a quick look. In the beginning, yeah, the acceleration is negative 10 meters per second every second. There's the height of the pineapple as a function of time, and you can see it initially is rising up from zero to a maximum height of almost 50 centimeters. The velocity graph for the pineapple starts off really fast, slows down and slows down and slows down until the halfway point of its motion when the velocity is temporarily zero. All right, as the pineapple falls, its acceleration is still the acceleration from gravity. There's the other half of the velocity graph and the other half of the height graph as well. You can see that the slope of the velocity graph is constant the entire time. Let's tell the whole story of the pineapple's acceleration from when I released it to when I caught it again. When I first threw the pineapple, its acceleration was g downward. A moment later, pineapple's acceleration, yeah, it's still g, it's still down. At the tippity top of the pineapple's path, the acceleration was still g and downward, as it was for the entire duration of the motion. That acceleration of g downward is the free fall acceleration of anything that's free falling on Earth. Regardless of its velocity or position, that's the acceleration. So let's look at a video of me rolling this very car up a ramp. It's going to start with an initial velocity up the ramp, but the acceleration is downward because the ramp is tilted. The car's acceleration is always down the ramp. That's to the bottom left of your screen. So just like with the pineapple, there are three phases of the car's motion. In the beginning, the car's velocity is up the incline and the acceleration is down the incline. The speed is decreasing. At the tippity top of the car's path, the velocity is momentarily zero. The acceleration is still down the incline. And as you see, the speed is zero.
So
the acceleration is still the same. As the car goes back down the incline, the speed is increasing. The car is getting faster and faster. The acceleration is still down the incline. So I created the same three graphs of the car's motion. That's constant negative acceleration, a position graph that starts off steep and levels off, and a velocity graph that starts at a high positive value and reaches zero. That's the whole first half of the motion. The second half of the motion, it's the same story as it was for the pineapple. Take a look at that velocity graph. Starts off fast and positive, becomes slow and positive. The velocity is temporarily, momentarily zero, and then it's slow and negative, and then fast and negative. So what should we take away? What's the big message here? Well, when an object's velocity and its acceleration are in opposite directions, the object's speed decreases. But when the velocity and the acceleration are in the same direction, the object's speed increases. And when something is in free fall on Earth, the downward acceleration is always 10 meters per second squared. It always points down. Gravity is always on. It's always down. And it's always 10 when you're close to the surface of Earth. When an object is on an incline and the only thing affecting its acceleration is gravity, then the acceleration is down the incline. An object's acceleration at a moment in time is equal to the slope of the object's velocity graph at that
acceleration at a moment
in time.
I'm definitely racking out after this.
The acceleration was constant and negative, and the velocity graph's slope was constant and negative. All right, what have we learned today? Well, I tossed a pineapple in the air and rolled a car on a ramp. The important thing was that I hope you realized that when the initial velocity of an object and its acceleration are in different directions, the object slows down, and that when velocity and acceleration are in the same direction, the object speeds up. We practiced the skills of creating graphs and supporting a claim using evidence. So we have wrapped up the most tropical AP Daily video so far. Thank you, everyone, for coming along. I look forward to working with you next time.
I wonder how much of that I'll retain. Alright, well I got 6 to get through in the morning because I got a free period. Thank you to whoever my single viewer is watching. Thank you for sticking with me. You're the reason why I was able to freaking, I don't know how long the stream is right now. But yeah. Alright. I'll catch you later.